200 million years after the Big Bang, not a single star existed, just hydrogen and helium drifting through total darkness. Then, gravity crushed that primordial gas into stellar monsters hundreds of times the mass of our sun. Stars that burned hot, died fast, and whose violent deaths shaped every structure in the cosmos. So how did a pitch-black universe produce the very first light? This silent era is known as the Cosmic Dark Ages. It began roughly 380,000 years after the Big Bang, immediately following recombination. At this moment, the superheated plasma of the early universe cooled enough for protons and electrons to combine into neutral hydrogen and helium gas. For the first time, light traveled freely, making the cosmos transparent. Yet no stars existed to generate new light. For over 100 million years, the universe expanded in absolute darkness. Pristine primordial gas drifted through a vast void, lacking any of the complex structures we observe today. There were no galaxies, no planets, and no heavy elements. But this vast, starless interval was an active arena of physics. Subtle differences in gas density, left over from the Big Bang, began to pull matter together along invisible filaments of dark matter. This setting poses a concrete scientific question. How did cold, uniform gas in an expanding dark void gather enough density to spark the very first nuclear fires? Gravity, not chance, directed the next phase of cosmic construction. The process began with tiny variations in gas density, where regions with slightly more mass exerted a stronger gravitational pull. Over millions of years, these areas drew in material from surrounding space. This primordial gas flowed along invisible filaments of dark matter, forming a vast, intersecting network known as the cosmic web. At the junctions where these filaments met, gas pooled into the universe's first gravitational wells, mini-hollows containing between 100,000 and 1 million times the mass of our sun. Within these dark matter cradles, the density of the gas rose steadily, initiating a fundamental physical conflict between gravity and thermal pressure. As gravity compresses gas, the atoms collide more frequently, causing temperatures to rise. This heating creates an outward pressure that resists further collapse. The threshold where gravity finally overcomes this thermal resistance is known as the Jeans instability. To pass this point and continue shrinking, the gas had to cool down. Yet, without heavy metals or cosmic dust to radiate energy away, the gas had only one mechanism available: molecular hydrogen. When pairs of hydrogen atoms bonded, they created molecules capable of absorbing kinetic energy through collisions and radiating it into space as infrared light. This slow molecular cooling eventually lowered temperatures to about 200 Kelvin. With thermal pressure deflated, gravity regained control, compressing the gas at the core of the mini-hollow into dense, isolated knots. Deep within these dark matter cradles, the compressed primordial gas reached a critical density, triggering the ignition of the universe's first stars. Known as Population 3, this inaugural stellar generation formed from pristine, metal-free hydrogen and helium. Unlike modern stars, these ancient giants grew to spectacular proportions, typically ranging from 30 to several hundred times the mass of our sun. Burning their fuel at furious rates, their surface temperatures climbed to 100,000 Kelvin, emitting an intense, brilliant blue-white light. They shone with the power of millions of suns, but this extreme brightness came at a cost. These massive stars exhausted their nuclear fuel in only 2 to 3 million years, a mere blink in cosmic time. Before they died, their immense radiative output fundamentally altered the surrounding space. They flooded the young cosmos with hard ultraviolet photons, carving out the first bubbles of ionized gas. Simultaneously, their emission in the Lyman-Werner band, between 11.2 and 13.6 electron volts, streamed into neighboring regions. This specific radiation destroyed molecular hydrogen in nearby gas clouds, stripping them of their cooling mechanism and temporarily halting the formation of sibling stars. While astrophysicists continued to debate the exact mass distribution of this first generation, their violent, energetic lives shattered the silence of the Dark Ages, initiating a complex feedback loop that would redefine the structure of the cosmos. The brief, brilliant lives of these stellar giants ended not in quiet fading, but in spectacular destruction. For the most massive stars, those between 140 and 260 times the mass of our Sun, the end came as a pair instability supernova. In these extreme environments, runaway thermonuclear fusion completely unbound the stars, tearing them apart without leaving behind even a black hole. This explosive nucleosynthesis forged the universe's very first heavy elements, carbon, oxygen, silicon, and iron, and blasted them into the surrounding intergalactic medium. Prior to these explosions, the cosmos contained only primordial hydrogen and helium. This sudden injection of metals fundamentally altered the physics of cosmic gas. Pristine gas could only cool slowly through molecular hydrogen, but these new heavy elements opened highly efficient cooling pathways. When gas metallicity crossed a critical threshold of about 1/10,000th of the Sun's chemical abundance, fine structure cooling by ionized carbon and neutral oxygen took over. This rapid cooling allowed gas clouds to reach much lower temperatures than before. With thermal pressure deflated, the minimum mass required for gravitational collapse, the Jeans mass, dropped precipitously. Gas clouds could now fragment into much smaller clumps, enabling the formation of lower mass, long-lived stars. These smaller stars could burn their fuel stably for billions of years, creating the foundation of modern stellar populations. Simultaneously, gravity drove the hierarchical assembly of the cosmos. Guided by the pull of dark matter, these newly enriched gas clouds and small stellar clusters drifted together along the cosmic web. Through constant, violent mergers, these small clumps coalesced into larger systems, building the very first primitive proto-galaxies and forever changing the structure of the young universe. Because astronomers cannot photograph the first stars directly, they trace them through an indirect trail of evidence. Cosmological simulations rebuild the early universe by evolving the laws of physics forward in time. In 2002, Tom Abel, Greg Bryan, and Michael Norman published a landmark three-dimensional simulation calculating exactly how a pristine gas cloud collapsed into a single massive star. Observational astronomers search instead for physical relics of this era. Through stellar archaeology, researchers like Anna Frabel and Norbert Christlieb examine the oldest dwarf stars in the Milky Way halo. Relics like SMSS J0313 6708 contain almost no detectable iron, preserving the chemical fingerprints of those first supernova explosions in their stellar atmospheres. At the same time, Hubble's ultra-deep views and the James Webb Space Telescope extend our observational reach to redshifts greater than 10, capturing the light from the universe's earliest structures. By analyzing spectra, measuring redshifts, and mapping specific absorption features, scientists connect these distant systems to local chemical fossils, confirming the physics of cosmic dawn. Radiation from these first luminous objects did not remain localized. It streamed into the vast intergalactic medium, initiating a patchy, uneven phase change across the cosmos. Extreme ultraviolet photons stripped electrons from neutral hydrogen atoms, carving out expanding bubbles of ionized gas. As these glowing pockets grew and merged, the cold, fog-like universe progressively cleared, turning transparent to light. To map this grand transformation, researchers analyze relic radiation. Measurements of optical depth from the Planck satellite constrain the midpoint of this transition to roughly 700 million years after the Big Bang. Meanwhile, specialized 21-centimeter radio experiments seek to detect the faint whispers of the remaining neutral hydrogen. How these bubbles spread, how quickly the fog cleared, and how efficiently these stars drove this cosmic awakening remain open, active frontiers of modern astrophysics, linking the first sparks of light to the colossal web of galaxies we see today. Today, the light of these primordial pioneers is finally reaching our telescopes. We are no longer just peering into deep space, we are witnessing our own origin story. The cosmic dawn isn't ancient history. It is the blueprint of everything we are. Subscribe for more cosmic journeys.